Greetings. My name is Zubair Mahmoud from Tokyo International University, Japan. Today, my presentation is about quantum teleportation, a very interesting and heated topic amongst the scientists around the world. Let's prepare to unravel the enigmatic nature of this entanglement. First of all, we need to know about what exactly is quantum teleportation. Have you ever dreamt of instantly teleporting objects from one location to another? While classical physics tells us this is impossible, the bizarre world of quantum mechanics offers a surprising solution: quantum teleportation. Teleportation is the process of transferring the quantum information of a particle from one location to another without physically moving that particle itself. Imagine copying the blueprint of an object, sending it through a special channel, and then reconstructing the object at the desired destination. This seemingly magical feat has profound implications for the future of technology. It paves the way for secure quantum communication, powerful quantum computers, and even a quantum internet capable of unimaginable feat. At the heart of quantum teleportation lies a fundamental concept: the qubit. Unlike classical bits, which can only be 0 or 1, qubits exist in a state called superposition, allowing them to be a 0 or a 1, or both simultaneously. This unique ability is what unlocks the power of quantum technologies. Think of a classical bit as a light switch, it's either on or off. A qubit, on the other hand, is like a dimmer switch. It can exist in various states between full brightness and complete darkness, offering a much richer spectrum of possibilities. In these two images, you can see a blotched sphere representing the state of a qubit on the left, and on the right side, you can see a comparison of classical and quantum bits using symbols of some visuals. Moving forward, let us now discuss about the core concept in quantum teleportation, which is entanglement. The key ingredient in quantum teleportation is entanglement. This phenomenon involves two quantum particles becoming linked in a way that their fates are intertwined, even if they are separated by various varying distances. Imagine two coins flipping the same way every time, no matter how apart they are thrown. Entanglement possesses two key processes and properties. So, before discussing the processes, let us only discuss about the properties here. So, one is non-locality. Entangled particles instantly correlate with each other regardless of distance. This means measuring one particle instantly affects the state of the other, even if they are separated by a light years of distance. The second property is measurements. Measuring one entangled particle instantly collapses the superposition of the other, revealing its state. This is the core principle used to teleport quantum information. In the following images, as you can see, there is an image representing the non-local connection between entangled particles, such as two coins flipping the same way simultaneously despite being far apart. In the another image, you can see a visualization of the Bell's inequality experiment setup. Next up is Bell's inequality. This is an experiment demonstrating the counterintuitive nature of entanglement. In 1964, physicist John Bell proposed an experiment that challenged our understanding of reality. This experiment, known as Bell's inequality, demonstrated that correlations between entangled particles cannot be explained by classical physics, providing compelling evidence for the non-local nature of the entanglement. The results of Bell's inequality experiment shattered our classical understanding of the universe, revealing a world where particles can be connected in a way we never imagined. This paved the way for our development of quantum technologies like teleportation of these days. This is a graph depicting the violation of the Bell's inequality, demonstrating the counterintuitive nature of entanglement. Moving on to our very interesting part of our presentation is where I'm going to discuss about the process of quantum teleportation. So, I would like all of you to imagine three characters: Alice, Bob, and Charlie. So, there are a couple of steps that you need to follow. It's number one, that preparation. Alice prepares two entangled particles known as pair A and B, entanglement. So Alice entangles pair A with the unknown quantum state she wants to teleport. Number three, Bell measurement. Alice performs a spatial measurement on pair A, collapsing their superposition and revealing a seemingly random result. And number four is the classical communication. Alice sends the results of her measurement to Bob through a classical channel like a phone call. And then number five, there is the operation. Based on Alice's message, Bob performs a specific operation on his particle, which is entangled with the unknown state. And number six, which is the last, is the teleportation. This operation magically transfers the unknown quantum state from Alice's particle to Bob's particle, achieving teleportation. For our better understanding and visualization, I have provided a couple of graphical and flowchart structure in my slide, which I have included. So what I have just said is kind of completely illustrated in these two images. So here you can see it's a flowchart or a diagram depicting the steps involved in quantum teleportation, including Bob, Alice, Charlie, and the entangled particles within there. So this is a much more detailed visualization of the process. Here you can see in the image a complete example of what I have just said. Take a moment and see the image, please. All right. So now we are going to discuss about the applications of quantum teleportation. Imagine sending messages that are unbreakable even by the most powerful computers. Quantum teleportation can be used to create quantum key distribution, a method for generating and sharing secret keys that are impossible to crack. In the recent times, the quantum teleportation has been applied to different sectors of quantum technology world. Starting from communication, where secure and reliable transfer of information is done, to building powerful computers for complex problems. There is also the use for connecting quantum computers across vast distances using quantum teleportation. And there is the quantum internet, a future internet based on quantum principles, which is now in laboratory use right now. All right, so right now we're going to discuss about the challenges and future directions of quantum teleportation. Scaling up, the current limitations in distances and fidelity is a major concern in this field. As you can see in the images, one of the major limitation for them will be the distance limitation. So there have been a lot of research going on regarding this, as well as we have discussed this in our class. So we are going to discuss this furthermore in the future as well. But for the time being, there is some visualization of progress to cope up with this distance or fidelity limitation in the picture at the right side. This technology is known as the quantum repeaters. Quantum repeaters are basically a landmark victory in the field of quantum technology. It's the technology for bridging the gap. Imagine whispering a secret across the globe instantly and unbreakable. That's the promise of quantum repeaters, the signal boosters for the quantum world. Like Pete's stops for information, these marvels amplify and regenerate fragile quantum signals, letting them travel farther than ever imagined. Why do we need them? Think of quantum information like a delicate butterfly. Over long distances, it loses its magic, its quantum superpowers. Quantum repeaters gently pick up this butterfly, carefully examine it, and create a brand new one, carrying the original message. How do it work? It's like a relay race with entangled particles, those spooky twins of the quantum world. One twin travels to the repeater while the other stays at home. By measuring the traveler, the repeater instantly knows the state of its twin at home like magic. This information is then used to create a fresh pair of entangled twins. One twin carries the message forward while the other stays behind, ready to receive the next whisper. This race continues, quantum butterfly hopping from repeater to repeater, crossing continents and oceans, and the impact is mind blowing. Unbreakable networks. Imagine sending secrets that even the most powerful computers can't crack. Quantum repeaters can make it possible. Then there is the possibility of improvement in quantum internet. Imagine connecting quantum computers across the globe, unlocking unimaginable computing power. Then there is the possibility of new discoveries. Imagine exploring the universe through the lens of a quantum entanglement device, unlocking mysteries hidden within the universe. Quantum repeaters are more than just technology, they are gateways to a future filled with possibilities unknown. The future of communication, computing, and scientific discovery rests on their shoulders. So let us get ready for a world where whispers travel the world and the impossible becomes reality. So, moving forward, despite all these powers and all these great, enormous amount of possibilities of quantum physics, as well as quantum computing, anything, we need to be careful regarding the use of it, regarding the misuse of it. When internet was first developed, it was developed as a technology. When atomic bombs were developed, they were just made for mining purposes. In fact, nothing in the world is created to destroy humanity. However, so because of our mind's complex structure, we tend to misuse this kind of technologies in a proper way, in a way that they are not meant to be created. They're not created by the creators for that purpose. So we need to be quite aware of this technology while using them in a proper manner. And for this technology, the main concern will be the cyberspace security. And then we're coming down to our end. So if you have any kind of question, write any comments below in the video and let me know. I will communicate with you all. Thank you so much. Have a nice day.